In this video, we will learn about batch reactors. To start with, what is a batch reactor? A batch reactor is a closed system used in chemical and biochemical processes where all reactants are loaded at the start and then the reaction proceeds over time and products are removed only at the end of the reaction. This is the schematic representation of a batch reactor. This batch reactor consists of a vessel along with the agitator, heating jackets and cooling coil. It has ports and nozzles. A agitator is installed inside the vessel to stir the reactants, ensuring uniform concentration. Jackets are used to supply steam and cooling coils are used around the reactor to control the temperature. Now let us make the following assumptions to develop the process model. First, the reactions which take place in this batch reactor are both exothermic. The reactor is well insulated such that there is negligible heat transfer in between the reactor and the external environment. Some parts of the cooling water and steam supply lines which are exposed to the environment are also insulated. The next assumption is the inlet and outlet coolant temperature do not vary much due to a sufficiently rapid flow rate of the coolant streams. Therefore, an average water coolant temperature, that is Tc, is used in the mathematical model. The condensed steam is discharged at its saturation temperature, meaning there is no subcooling. We assume constant volume V reactor with constant mixture heat capacity Cp. Note that here the volume refers to the volume of reaction mixture, not the volume of the reactor. The reactor contents are perfectly mixed and do not exhibit significant gradients of species concentration or temperature in any part of the reactor. The overall heat transfer coefficient for heating jacket Uj is assumed constant, but the overall heat transfer coefficient for the cooling coil Uc is assumed to be a function of coolant flow rate, that is Fc. The balance equation, that is mass balance and energy balance of batch reactors. First, mass balance equation. Rate of mass in minus rate of mass out is equal to accumulation. Here, rate of mass in is equal to 0 as well as rate of mass out is equal to 0. The accumulation is d by dt into rho v. On balancing this equation, we arrive at the final equation of rho dv by dt is equal to 0. Now, let us see the component material balance. The general formula is rate of mass in minus rate of mass out plus rate of mass production by generation due to chemical reaction, which is equal to accumulation. Now let us see the component balance for material A. Here generation is equal to Ra, accumulation is equal to d by dt Vca. By doing the balance, we will arrive at the final equation of dCA by dt is equal to minus K1 Ca square. Here Ca is the concentration of A and K1 is the rate constant. Similarly, let us do the component balance for material B. 0 minus 0 plus Rb is equal to d by dt into Vcb. By further simplifying, we arrive at the final equation of dCb by dt is equal to K1 Ca square minus K2 Cb. By using the Arrhenius law, we come to the point that K1 is equal to K01 e power minus e by RT. Similarly, for K2, K2 is equal to K02 e power minus e2 by RT. dCA by dt is equal to minus K1 Ca square. The final equation is dCA by dt is equal to minus K01 e power minus e1 by RT Ca square. Similarly, for component B, dCb by dt is equal to K01 e power minus e1 by RT Ca square minus K02 e power minus e2 by RT Cb. Let us see the energy balance. The general formula is flow of internal, kinetic and potential energy into the system by convection or diffusion minus flow of internal, kinetic and potential energy not into the system by convection or diffusion plus heat added to the system either by conduction, radiation, and reaction minus work done by the system on the surrounding, which is equal to time rate of change of internal kinetic and potential energy inside the system. This is represented by Uj Aj into Ts minus T minus Uc Ac into T minus Tc plus minus delta H1 into K1 Ca square V plus minus delta H2 K2 Cv B is equal to d by dt into V rho H. By further simplification, we finally arrive at the equation of dt by dt is equal to uj aj into ts minus t by rho cpv minus uc ac into t minus tc divided by rho cpv plus minus delta H1 into K1 Ca square divided by rho Cp plus minus delta H2 K2 Cb divided by rho Cp. Here Uj is the overall heat transfer coefficient for heating jacket. Similarly, Aj is the overall heat transfer coefficient for cooling coil. Ts is the steam temperature and Tc is the cooling water temperature. This is how we derive the mass balance and energy balance equation for a batch reactor. Now let us see the advantages, limitations and applications of batch reactor. Advantages: flexibility, easy to switch between different products or recipes. It is good for small scale production, ideal for making specific chemicals, pharmaceuticals or prototypes. High conversion possible. You can let the reaction go longer to achieve high conversion of reactants. Simple design and operation. Disadvantages of batch reactor. It is labor intensive, low productivity for large scale, difficult to control quality consistency, high operating cost. Applications of a batch reactor. Pharmaceutical industries, drug manufacturing where small volumes and strict quality are required, food and beverage, specialty chemicals, dyes, perfumes, additives where customization is important, biotechnology, research and development.